Hi, I'm Ke-Xin. In this short video, I'll give you a quick look at our work on learning interpretable and editable policies with our neuro-symbolic model called Neural DNF-MT. The motivation of this work is to improve the interpretability of RL policies. It is important to know what the learned policies actually are when applying RL in high-stake decision-making, such as healthcare. Black box neural models are not so appealing in these scenarios, but policies that can be understood by humans are greatly beneficial. Apart from just being human readable, interpretability makes intervention on the policy much easier. Many neuro-symbolic RL approaches exist to improve the interpretability of policies, but there are a few drawbacks. Many use rule templates or mode biases to restrict their search space, but also restrict the forms of the policies the models can learn. Useful predicates fed into the model are either human engineered or extracted from pre-trained models, so they are not learned and less flexible. We propose our Neural DNF-MT model for learning interpretable and editable policies, while giving a lot more freedom to the model compared to existing neuro-symbolic RL approaches. Our model is trainable in standard deep actor-critic algorithm, fully facilitating end-to-end training for both learning policies and doing predicate invention without human engineering. Our model is interpretable by providing logical representation of the learned policy. We can represent a stochastic policy in probabilistic logic and a deterministic policy in bivalent logic. Our model has the property of bidirectional translation between the neural model itself and its bivalent logic representation. So we can modify the ASP policy representation and inject the changes back to the neural model. This is very beneficial for inference because inference in neural models utilizes tensor operations and environment parallelism, making it much faster than inference in pure logic. Here we show two setups for training the Neural DNF-MT actor in a deep actor-critic algorithm. Our actor network is the Neural DNF-MT model and outputs action probabilities. We have a simple MLP critic with usually 2 layers that gives value estimate. On the left is the usual setup if the observations are already discrete, and on the right is the adaptation for predicate invention, where the observation can be quite complex, like this multi-dimensional matrix here. We want to learn some useful predicates before feeding them to the actor. Here we use a simple convolution layer with a linear layer as an encoder for predicate invention, and in principle we can also add more layers to this encoder or swap it with a more complex neural architecture for the same purpose. Now I will show an example of policy learning with our Neural DNF-MT actor in an environment called door corridor. This corridor is inspired by mini-grid and has the same observations space as other environments in the mini-grid set. The agent in this right triangle here sees a 3x3 grid around itself, and the vision can be blocked by obstacles like walls, gray cells here, and also closed doors. This door here right now is closed. The agent's goal is to reach the green cell at the end of the corridor here with 4 possible actions: turn left, turn right, move forward, and toggle. Toggle only works on a door and flip the status of the door. This is an example of the policy learned by a Neural DNF-MT actor represented in an ASP program. We see that only 3 actions are used by the agent to reach the goal, and each action is triggered with different body conditions. These predicates A's are the invented predicates from the encoder, and the definitions here are computed using ASP optimization function, so now they're also human readable. And to demonstrate the editability of the policy, we modify the base door corridors to 2 variations, where we change how the agent needs to interact with the goal state to finish the environment. DCT requires the agent to not step into the goal state, but to toggle it. DCOT requires the agent to do a toggle when it's already on the goal state. We can edit the ASP policies quite easily, and with the edited policies, the agent can immediately pass the 2 modified environments without any retraining. And of course, as mentioned before, we can port these changes in ASP policies back to the Neural DNF-MT models so that we can still inference with neural architecture in parallel environments. And that's a quick look of our work. If you're interested in our work and want to find out more of our Neural DNF-MT model on how it works, results, analysis, and so on, please refer to our full paper. The preprint is available on arXiv, and this QR code here will take you there. And thank you very much for watching this video.